Okay, in this video, we're going to chat a little bit more about our integration techniques. The test that we were going to take this week, I'm just going to go ahead and switch to a take-home version. I'll trust you all to complete these honestly. In class today, we were going to review one more time prior to the test. So what I've done here is I've taken the take-home portion of the test itself, and I've selected a handful of problems to kind of demonstrate here in this video, and then let you use that along with your other practice to prepare for the take-home portion of the test. So as you can see, I've blocked a few of these out, so I'm only going to focus on the ones that I haven't. Now, my intention on this particular document was to indicate the methods that I want you to use for solving each of these integrals, so please do use those. I think the techniques are pretty straightforward, especially having had the practice over the last several weeks. Hopefully you're familiar with each of them. The only one that's kind of interesting are the trig substitutions. Remember in class we had we had a chart, and I think I pulled that one from Math Excel. But there's a chart that helps you recognize which trig substitution to use and which trig identity would be helpful for having that. So if you haven't already located that chart, please do so. I have it actually here in OneNote. This is the one that we were referencing in class. So if you need to take a screenshot of this or write this stuff down, that's fine. Or find your own copy that you've been using in the past. That way, this, along with whatever other small amounts of reference material, can be used on the test, and you won't have to reference anything else while working on it. Speaking of expectations for this test, I did put a series of ground rules in a list together, and I've sent that to you in an email. I've also posted it to Cincinnati State's website, so please make sure that you're abiding by those rules when you're working on the test itself. So without any further delay, I'm going to go ahead and start working on these selected problems. Okay, in number one, we're told to use the u substitution method to find the indefinite integral, and we must identify u and du. Well, in this case, I'm going to use a u value of x squared plus 13, since that's on the inside of an inner function. So the derivative of this ends up being 2x with respect to x. Now you can isolate the dx to help you with your substitution, but since the 2x and dx is present already, I'm just going to create the direct substitution. And so that leaves me with now an integral of u to the 5th power with respect to u after making our substitution. And the antiderivative of u to the 5th ends up being u to the 6th divided by 6 plus c. Of course, we'll need to back substitute, and we'll call this x squared plus 13 quantity to the 6th power divided by 6 plus c. And we'll call that good from there. Now, I would not recommend on the take-home portion doing what I've just done here and writing your work squeezed into the the printout like this. Make sure you do your work either on a separate sheet of paper or create a blank page in OneNote and then show all of your work there on lined paper. I think that'd be a lot easier for me to score, and hopefully a little bit easier for you to follow and keep track of your own work. Now on this example, we are using the integration by parts method. So that's the one that looked something like this. The integral of u v prime is equal to uv minus the integral of v u prime. Got to be careful with the way I write that. So that was the integration by parts design. If we select u and v prime carefully, then the initial integral decomposes into something a bit more manageable. So for this case, I'm going to let u be equal to x, and I'm going to let v prime be equal to sine of 1 over 11x. I'm just going to call that as x over 11 here. In case you forgot, there was that acronym ILATE, or LEATE is the way it's sometimes written online. inverse equations, logarithms, algebraic, trigonometry, and exponentials. Those are the order of types of problems that I would consider for my u value. Since x is an algebraic expression where sine is a trig expression, I'm going to use the x as my u value because the algebraic expressions came before the trigonometric expressions. If that's not familiar or if you forgot that technique, please make sure that you look that up before you begin this test. So if we select u to be equal to x, then the derivative of u is equal to 1. If we select v prime to be sine, then v, the antiderivative of that, is some form of cosine. Now this does take a little bit of thinking here. The antiderivative of sine is negative cosine, and the fact that we've got this 1/11th multiplier on the inside, we have to counteract that. So I'm going to put a coefficient of 11 in front of this cosine. So with that prep work done, we can now state by the integration by parts that this original integral is actually equal to u times v. So we now have x times negative 11 cosine of x over 11 minus the integral. Now this is why the parts method is nice. We're going to multiply by u prime and v. So u prime ends up being the number 1 times v, which is negative 11 cosine x over 11 dx. Now this 1 times negative 11 doesn't really do anything, but if we simplify this just a little bit before we proceed, I now see negative 11x times cosine of x over 11. This negative sign multiplies by this negative 11, so I'm going to call that plus 11 times the integral of cosine x over 11 dx. We'll copy down this expression again, so we have negative 11x cosine x over 11 plus 11 times, now the antiderivative of cosine, x to the 11, or x over 11. Similar to what we did over here, antiderivative of cosine is sine. And to offset this 1/11th on the interior, we'll multiply that by 11. And finally, we can clean this up, 11x cosine x over 11 plus 121 sine x over 11 plus c. And there's our antiderivative using the integration by parts. For this next example on the trig substitution, if I consult my summary document here, we're in this format, so we have this x squared minus a squared form. I'm going to let a be equal to 15, and then therefore, because of this format, I'm going to use this substitution for the letter x. I'm going to rewrite x as that a value times secant of some new value, some new variable theta, representing an angle on a triangle. So again, these trig substitutions get to be kind of interesting, but they are, I think, quite neat when they work out well. So for some preliminary work, I'm just going to make some notes here. I'm going to let my a value be 15. I'm going to let my x value then be 15 times secant of theta. And while I'm here, I'm just going to note that if x is equal to 15 times secant theta, then secant theta by itself is equal to x over 15. And now we've got the side length ratio associated with normal trig expressions. That'll be helpful for us to see a little bit later. Also, while I'm here, the derivative of x ends up being 15 times secant theta times tangent theta, d theta. So this derivative is going to be helpful when we utilize the trig substitutions as well. So there's some preliminary work. Let's make some substitutions. This equation, when I change x to this expression and dx to this expression, we end up with the integral. Now I do kind of like the way dx is written on top of this fraction here. Normally I would ignore that, treat that as a 1, and put the dx off to the side. But this time it ends up working out pretty nicely, because with the dx in the numerator, when rewritten, I have now 15 secant theta tangent theta d theta over the square root. Now my x squared is getting replaced with this x, and I'm squaring it, so I'm just going to call that one, oops, I'm just going to call that one here we go. All right, 15 squared secant squared. So that takes care of my x squared minus 225, and I'm going to call that one as 15 squared. So again, on our reference sheet over here, there was a note that if we see this format, a number squared, secant squared minus that same number squared, we can then use a trig identity to rewrite it as a squared tangent squared. So with that in mind, we'll make some modifications to the next line. We still temporarily have, this 15 secant theta tangent theta. And by the way, that was a derivative rule that we had learned in in Calculus 1. Now we have the 15 squared tangent squared theta. But since this square number is underneath a square root, let's see here, I'm going to be running out of room, so I'm going to dive over here. We can now report this as the integral of 15 secant theta tangent theta over 15 tangent theta d theta, with the simplification in the denominator. Then we end up with the 15s that cancel, the tangent thetas that cancel, and now we're at a point where all we need to do is find the antiderivative of secant theta d theta. And while that looks nice and simple, you may think that that's familiar or something that we've memorized in the past. Please remember that we know the antiderivative of secant squared to be tangent, but secant by itself is not quite that simple. So for this one, I'm going to refer back to the table of integrals, and I'll note that on number 7, we do have the antiderivative of secant provided to us. It's the natural log of the absolute value of secant plus tangent. So that one's a little bit, it's interesting. It's a little tricky because it's not quite so obvious as one might hope. But you know what? We're really close to the end now. We're going to report that the antiderivative of secant is the natural log of the absolute value of secant theta plus tangent theta plus c. And we're almost there. We're almost in our home stretch now, but we have the antiderivative in terms of theta. We really want to report our answer in terms of x. So the original variables were x, and that's what our instructions are asking for. So I'll just remember with this piece of information, if secant of theta is equal to x over 15, well, that tells me that we're kind of related. We have some side lengths related inside of a right triangle. Now, secant is the description of the opposite side length, the hypotenuse divided by the opposite side length. So our hypotenuse is x, and our side length opposite of the angle is 15. Wait a minute, I got that mixed up. Secant is the reciprocal of cosine. So I want 15 as my adjacent side. There we go. So our adjacent side is 15. Our hypotenuse length is x. So we can find this missing side length using the Pythagorean equation. Hypotenuse squared minus 15 squared. That's kind of interesting because that's the exact format that we were looking at earlier. Some x squared minus a squared. And so if we return back to what we have here, we can note that the natural log of secant theta, we described secant theta as x over 15. Now tangent theta, when using this triangle as reference, would require our opposite side length to be divided by the adjacent side length, which is root x squared minus 15 squared over 15. Retain the constant of integration, and now we have our antiderivative in the original variable. And I would leave that as it is. I wouldn't bother combining these fractions into a single since they have a common denominator, and I wouldn't simplify the 15 squared to 225. I would leave it just as it is. Okay, with two more to go, let's talk about this partial fraction decomposition. That's the one that said that we should consider factoring, if it's possible to factor, especially in the denominator. We can factor the denominator into its pieces and then find sum of several smaller fractions to compute the antiderivative of. So in this case, considering the numerator here, it looks like this is a factorable quadratic, but the outside product multiplying to 4, requiring those same factors to sum to 12, I don't think that can happen. So we're going to leave that as x squared plus 12x minus 4 in the numerator, but it's the denominator that I'm really interested in. We have x as a GCF times x squared minus 4. And then immediately we should recognize that x squared minus 4 factors into x plus 2 and x minus 2. So there's the original problem rewritten in its factored form. We can use the cover-up method to find our a, b, and c values, because the claim is that this fraction as written could actually be some number over x plus another number b over x plus 2 and added with some c value over x minus 2. So even though we have a product in the denominator in the original expression, this partial fraction decomposition is going to separate that into 3 smaller fractions that are all added together. Now our job is to find out what a, b, and c are. We can use a system of equations, but as I mentioned just a minute ago, we're going to use the cover-up trick for this one. So to find a, we cover up the base here and imagine what number would set that equal to 0. Well, that number is 0, so for a we need 0 squared plus 12 times 0 minus 4 over the remaining expressions, 0 plus 2 times 0 minus 2. Well, this numerator turns into negative 4, the denominator turns into negative 4, and we end up with 1. So this a value would have to be 1. Similarly, for b, we're going to cover up the b factor. The number that would make that 0 is negative 2. So I'm going to go through the exact same process, but I'm not going to really show it here. And in the interest of time, we'll just kind of condense the work. I end up with a negative 24 in the numerator and a positive 8 in the denominator. So my b value ends up being negative 3. And then finally for c, same thing. We would cover up this c value, or the c denominator. The number that makes that 0 is a negative 2. So when we substitute a negative 2 into these expressions, we end up with a positive 24 divided by 8, which leaves us with a positive 3. So now we have 3 integrals that are much easier to manage. Negative 3 over x plus 2 and positive 3 over x minus 2. And we can approach the antiderivatives from here. So the antiderivative of 1 over x is the natural log of the absolute value of x. The coefficient of negative 3, I'm just going to push that out to the front. And the antiderivative of 1 over x plus 2 is just the natural log of x plus 2. It's nice that there's no coefficient here to manage or to modify. And then finally, 3 times natural log of the absolute value of x minus 2. And each of those antiderivatives had a c value that I've now combined into a single c value at the very end. We have our constant of integration. Now, the last example that I wanted to work through in today's video as our final review is this one here. This group of instructions said to use any method necessary, so we can use any of the 4 methods that we just tested you on before. Let's not forget about trig identities, which is actually what I'm going to use here for this example. And we'll just try our best to find the antiderivative. Now on our trig identity sheet, either from this class or from trigonometry, there's a particular trig identity that's helpful here. It's one of our double angle identities, and cosine comes in a couple different varieties, but this is the one that I like because while it's 2 cosine squared minus 1 out front, I can add 1 to both sides, and now I have that 1 plus cosine 2 theta ends up being 2 cosine squared theta. Those two are equivalent expressions. We have this in our original problem, so I'm going to use this trig identity to make the substitution here. And so I don't need to change the variable at all. I'm still going to integrate from an x value of 0 to an x value of pi over 2. But now I have the equation square root of 2 cosine squared theta. Oops, sorry. I'm not changing the variable. So cosine squared x dx. And this is particularly nice because, well, the square root of the product of two terms is just 2 of those square roots. So now I have a square root of 2 times cosine x. So the square root of cosine squared is x. And square root of 2 is just a coefficient, so I'll push that out to the front. The antiderivative of cosine is sine. And when we evaluate sine at our boundaries of integration, 0 and pi over 2, we have root 2 times 1 minus 0. Sine of pi over 2 is 1. The y value at pi over 2 is 1. And the y value at 0 radians is 0. So sine of x evaluated at these two boundaries is 1 minus 0. And we end up with just the square root of 2 times 1 minus 0. And we'll call that square root 2. So I think that's the last of what I wanted to review in this video. On the take-home portion, there is a backside to the handout, and these are really just kind of some review questions on the fundamental theorem of calculus, and then our ability to change variables. We have a graph where an equation is written in terms of x, and we'd like for you to set up the integral to solve that area problem in terms of x, but then also rewrite the equation in terms of y and solve the integral, or set up the integral. Sorry, don't have to solve it, but set up the integral and in terms of y. So I misspoke there. We are asking you to calculate the area. So we do want you to set up the integral and solve. But if you didn't notice, I did include a comment here. Calculator permitted on that one. So if you have your, oh, you know what? I didn't even realize this. We did indicate calculator permitted on a couple of these questions too. So, well, if it says calc permitted, go ahead and use the calculator. Check your work, I would say, doing it that way. I would really like to see your setup, though, because I know that all of these can be solved without the use of a calculator. So anyway, on the back side, though, once you get your integral set up, certainly use your calculator to evaluate the integral or several integrals, and that'll help verify whether your approach was correct, because the area in either case should be the same. Reach out to me with questions by email. That's going to be the best way to get a hold of me while we're working from home today. Thanks a lot for watching.